Is a higher quality battery worth paying for, or is a cheap Chinese alternative worth it? And is it even safe? Today we're talking drop-in lithium iron phosphate batteries, and you can find a lot of different options out there these days that offer similar capacities and specifications, for lots of different prices. So what really are you paying for in a higher priced battery? Today, we're gonna find out. I've got 5 different battery brands here that I'm going to be tearing down and doing a comprehensive set of tests on. Now, I've selected these brands because I believe they represent a wide variety of designs and cell types that you're gonna find in most drop-in lithium iron phosphate batteries. While this is gonna be a head-to-head comparison, lots of charts, information, and data about that, I'm also gonna be just kind of looking at the wider design choices for reliability, safety, and longevity. All of the tests are going to be done with the batteries torn down so that we can both physically and in thermal IR see what's going on inside these batteries, as well as electrically with probes and meters, so that during the tests we can really see what's happening. Now, before we get going, an important disclosure: Battle-Born Batteries, which is in our lineup today, is and has been a sponsor of this channel for many years, and we use these batteries personally. However, personal bias aside, I am doing all of these tests independently from Battle-Born Batteries. This is my shop, my test equipment, and I've controlled the purchasing of all of these batteries. I am genuinely curious to actually dig into these different brands and learn more about them, answer a lot of my own questions, and some questions that have been raised by viewers of past videos. I've standardized my tests to the best of my ability so that we should be comparing each of these batteries on similar footing. I will be sharing some of my personal opinions on different things, but the data at the end will be fair. Now, a fair warning, this might get a little bit technical. I am an electrical engineer and I love to get into the details and nerd out on things. I will do my best, however, to distill down the most important things and what it means for the end consumer. My specialty is in high-powered industrial design for safety and reliability, and I'll be bringing some of that mindset down to look at these batteries. If it's not safe, it's not worth having, and if it's not reliable, use case is really gonna have to be thought out. I've built lots of battery systems, both grid tie and off-grid, and I'm really excited to do these tests. Now, you may have noticed that behind me over here, I've got a second set of all of these batteries, and that's because we're gonna be testing these batteries at and near their limits and pushing them beyond a little bit. They technically should be able to handle all that, but it is possible that we could break something, and I want to be able to continue the tests if that happens. Also, in a second follow-up video, I plan to electrically and physically push these batteries beyond their limits to see what happens. And at that point, we will break things, and we'll probably even see some fire. We'll be talking a lot about safety in this video, but even more so in that follow-up video. I am super excited to get into this, so let's do it.
Before we start testing these batteries, let's learn a little bit more about them and tear them down to their components. First up is the Dakota Lithium that costs $719 per battery, claimed 100 amp hours and weighing in at 22.8 pounds. Overall, one of the smaller batteries we're testing. Dakota's listed as a US company, with its parent company being Clean Republic, who's an importer of lithium batteries and hilltopper bikes from China. They claim these packs UL 1642 listed, and also claimed IEC 62133, but I could not find any certifications on UL or Intertech databases for this pack.
Okay, I know we're just getting going, but I want to stop and explain a few things here and there. First, I want to talk about certifications. Certifications, also known as listings, are when a product has been tested by a third party, similar to what I'm doing here, to ensure the product is safe. It's not going to cause harm to you or property damage. There's lots of different certification agencies. Here in North America, we primarily rely on UL, Underwriters Laboratories, or Intertech for our certifications. There's German certifications, European certifications, Chinese certifications. There's all kinds of different certifications. But depending on where you're at, there's specific certifications we're looking at. If you look at the back of a lot of products, you're going to see a CE, an FCC, a UL. Those things are stamps that say this product has been certified, but they don't always mean the same thing. There's basically many different certification standards that a product has been tested to. And testing a product is usually very expensive for the manufacturer, and also means they can't then change that product going forward in the future because you have to buy the product that was certified. In the past, most big retailers wouldn't sell products that weren't certified, so we were buying mostly certified products. But recently, with the advent of online sales, and for many other reasons, which is a whole nother video, non-certified products are getting into our homes more and more, and the onus to buy a product that's actually been tested is more on the consumer than ever before. Well, it's really up to you whether you purchase a certified product or not. A lot of times for companies, it's not an option. For liability purposes, a lot of times a company can't get insured, or if they have an incident, the insurance won't cover it if they were using uncertified products. Overall, purchasing certified products is generally good practice because you know you're getting a product that has been independently certified by a third party. Again, here in North America, that's primarily Underwriters Laboratories or Intertech, and also the FCC database, where most of our electronics have to go through to make sure they're not going to cause interference or problems with our electromagnetic spectrum.
The design has epoxy terminals, which have nifty little handles on top. However, the top of the battery was easily removed with minor prying with only a screwdriver. It seemed the glue was lacking and this battery was not completely sealed.
Opens surprisingly easy.
The battery was secured in the rest of the case quite well with some glue and stuck down on the bottom with some double-sided tape that required me to cut away the side of the case to pry it out.
So I can't open this all the way because I don't want to damage anything, but basically this is designed as like a fold, so the bus bars come all the way over, fold over, and then the cells are in a series parallel configuration just right in the bus bar. It's an incredibly space-efficient design. I've seen this manufacturing technique used before. It's relatively quick and pretty common for a lot of these Chinese packs. Our temperature sensor was just kind of shoved up inside the cells here, and then you can just kind of see a really densely packed cells.
The battery is a cylindrical cell design with 80 cells, a 20 parallel 4 series configuration. I was able to look up the cells. They're 26700 5000 milliamp hour cells from Chinese company Hisun. Doing a little more digging on Hisun, I found that the pack is most likely a rebranded Hisun pack directly from China, as they sell packs of their batteries that look just like this, with the same sizes and specs, just lacking the red, white, and blue. They also offer many other sizes of packs matching much of Dakota's offerings. With this information, I did search the listings once more, and did come up with an Intertech Hisun listing for this pack, showing a UL 2054 certification. The BMS I was easily able to look up on Alibaba, and found it available for around $40. The BMS claims Bluetooth functionality, which I was able to see on my phone, but Dakota makes no reference to. Next up, the second from the cheapest pack at $649 is the Renogy 100 amp hour smart battery. Weighing in at 23.3 pounds and with dimensions that are not quite square, with about 0.2 of an inch taper top to bottom. Renogy is a trade name for RNG International that mainly imports its products from China. The battery claims Intertech Standards certification UL 1973, which I was able to verify. This certification is a general set of tests similar to what we're going to be doing here today to verify safety. This battery is a little bit different in that it has a Cat6 type connector terminal on the top, which requires a special little button to be inserted to turn it on and off. The battery is held together with screws that, once removed, the lid simply lifts off. A few more screws and the battery easily separates from the case. A stainless steel inner case holds the battery together, and some more disassembly revealed the cells themselves. I was not able to find any specific information on these cells other than general information about pylon.
With Renogy torn down, we can see these are a pouch cell, PY Li-ion battery. There are 8 cells, a series parallel configuration, and this is kind of funky. They're actually doing the connections with these big blobs of solder. And then we have a gigantic heat sink on the BMS, which sits on top, and lots of stuff communicating both into the top of the battery and the down to the BMS balancing leads, which must go into each one of these on the back side of this, which I'm probably not going to take. I can't take off because it's physically soldered on, and those solder points are actually what hold this whole thing together as well. This one also has a heated pad right here on this side. That's just disconnected like so.
Overall, pouch cells are considered the least robust and require this additional stainless steel case. The Battleborn B1012 is the most expensive of the batteries we're testing at $925. It's also the heaviest, weighing in at 31.1 pounds. Rated at 100 amp hours, this is a slightly larger pack as well, and like the Renogy, had a slight taper from the top to bottom. Battleborn batteries are the only ones we are testing that are assembled in the US. Their factories in Reno, Nevada that we have been able to visit in the past to see the construction process. Battleborn has UL certifications that I was able to verify, UL 62133-2 and the more general UL 2054. 62133-2 is the most stringent lithium-ion specific certification for safety I have found and the only battery in our testing that has been certified to this standard. Interestingly, I also found that this battery had a non-incentive Class 1 Div 2 certification, basically meaning it's certified not to be an ignition source when in a flammable environment. Battleborn has brass terminals intended for bolting to that are sealed in epoxy. I started disassembly with a chisel, but quickly realized the top would not easily come off. An oscillating multi-tool was used to cut through the case. The battery proved to have the thickest plastic case and the best sealing of all the batteries we tested, making it difficult to open. It took me some time to figure out the epoxy terminals on the top part were actually part of the structure and had to be cut out separately. I believe this battery to be the best sealed of the ones we tested and probably even capable of being submerged without ingress.
So those are just rubber spacers. It's actually pretty heavy, all that stuff. That's just to pad the battery inside the... There we go.
The pack is constructed of 120 26650 cells in a 30 parallel 4 series configuration. With a little research, I was able to find the manufacturer of the cells. They are Chinese cells, but Battleborn has a relationship with them to oversee quality. For the cells, I was also able to find a UL BBFS2 listing for the cells themselves, demonstrating them as safe. This makes Battleborn independently UL certified at both the cell and pack level. The BMS for the battery sits in the slightly elevated top portion, and I could not find any specific information on it, and believe it's a custom unit for this battery. It has 5 soldered 10-gauge wires connecting it to solid copper collecting bus bars at each end of the cells. The 30 cells in parallel form individual 3.2 nominal 100 amp hour cells that are bolted together at the top. Individual cells are welded to plates at each end of the larger cells.
So this right here is a weird design of the Battleborn. The positive bus bar transmits the power through this bolt, but all of the power has to come through this nut. That's the only way it can get across there. And while that seems really strange, I talked to them, they said it was actually a intentional design, because if this gets too hot, it will melt this plastic, pull away from that, and disconnect. So even if everything goes down here, they kind of have a last line of protection right here, which none of the other batteries have anything like that. They will just destroy themselves. So that's kind of an interesting thing with the Battleborn. Okay, another quick aside. I know I've mentioned a lot about the BMSs that typically sit on top of these batteries, but what are they? BMS stands for Battery Management System, and this thing sits between the battery and the power that you're connecting to, and basically makes sure that everything is within spec. In general, lithium-ion batteries are very safe if they're used within the parameters that they are designed for, but if they get outside of that is when problems can arise. This thing basically says, is the battery being used appropriately? Stop using the battery, or yes, it's okay. And it's doing all these different checks. It's really just there for safety. In theory, you don't need it. The battery, if it's being charged properly and used properly, you don't need this thing at all. It's there as an additional level of safety. And we're gonna check and make sure that it's doing all the things that it's supposed to do to protect the battery from dangerous situations. But in theory, you don't actually need these. If, however, something goes wrong with this, it can invalidate the entire battery. So it is very important that the BMS does its job and is reliable.
Next, we take a look at the cheapest battery by a large margin, the LiTime. The LiTime I got for $251 on Amazon. Before we even get into this battery, one thing I noticed about receiving it was that while the box was labeled appropriately for lithium, the battery did not ship with hazmat paperwork as is required. All the other batteries I received had appropriate paperwork, but this one was missing, making me think that they are not properly shipping these batteries, possibly reducing their costs in this regard. This battery claims 100 amp hours, although I was not able to find any certifications in the UL, Intertech, or CE databases for this battery or any LiTime product. The battery is very light at 21.9 pounds, but physically the largest of the batteries we're testing. The lid of the battery did not come off easily, so I once again had to cut open the battery and found it actually was glued on quite well. The terminals are not potted, so I don't think its ingress protection is as good as the Battleborn, but better than the Renogy or Dakota. With the lid off, we could see the battery and BMS, and it's actually far smaller than the case, but supported with massive foam blocks, keeping it away from the edges. I had to cut one side of the case away and pry it out as it was glued in.
So the LiTime is a set of 4 prismatic cells in series. They are on their side, and this foam has holes for the vents. Prismatic cells on their side are a little concerning to me because you'd never want to install these upside down, and you could accidentally do that with this battery pretty easily. So that's an interesting use case. They do have, this is the first branded BMS we've seen. So be it that they're a Chinese company all the way through, they probably can easily white label these BMSs.
The cells are bussed together with large busbar connections. I was able to use an app to decode the cell information from the QR codes etched into the cell and discovered these cells to be from manufacturer Great Power and manufactured within the year of purchase. All the cells came from the same manufacturing run, except for one that was a completely different run, which I thought was interesting. Because of the potential for these cells to be installed upside down, I went through the literature that came with the battery and did find a warning saying not to mount it outside without contacting the company, which I was happy to see. Last up, in the second most expensive battery, is the Lion Energy UT at $25 cheaper than the Battleborn for a $900 purchase price. The battery is rated like the others at 100 amp hours and 100 amp discharge. Weighing in at 23.3 pounds, it was also one of the smaller batteries we're testing as a whole. The battery has a neat little set of handles built in and a fancy power meter on top. No certifications were able to be found on the product, but plenty of specs are printed on it. This battery came with very tall posts that can be removed. Embarking on disassembly, I originally started prying the battery apart before I realized it was actually screwed together. The screws were just covered in little caps. Once all the screws were removed, it easily opened up. The battery did have a decent rubber seal on the top, and the cells were quite difficult to remove as they were glued in, and the case actually had some support for the cells.
All right, a few things to note on the Lion. The BMS seems to have one of the most robust heat sinks of the batteries we've looked at. Interestingly, there's a little coin cell battery on the BMS. What happens if that dies? I don't know. Maybe I'll have to pull it out and find out. This one seems to have the most temperature sensors. There's a temperature sensor on the most positive and negative terminals on the cells, and also up inside each one of the actual terminals on top of the battery. There's a temperature sensor in each one of those. We've got 2 number 6s off each lead and down to the BMS, and all the wires are wrapped in this thermal material. They seem to be a high temperature silicone as well. The Bluetooth module seems to be up on this side, and then this is, I think, just the little state of charge indicator on the top. On the top here, we do have these little bumpy things. I'm guessing these are soldered or welded, and there is no strapping or compression, so that must be done by the case. There is also some separators between the cells, which probably would allow for a little bit of expansion and contraction. The cells are standing upright, allowing for their vents to point the correct direction.
Like LiTime, these are prismatic cells and had QR codes, allowing me to scan and look up the cells. These cells turned out to be EVE02Y cells, rated at 105 amp hour capacity each. EVE is a Chinese manufacturer of prismatic lithium cells. I did run a UL listing check on these batteries and found these cells listed with BBCV2 and BBGA2 UL listings. All the cells came from the same factory and the same run, but they were manufactured in October 2021, making them 2.5 years old by the time they were sold to me in the pack, which I found a little surprising.
All right, quick overview of all the batteries. Now that we got them all torn down, the Lion Energy is running 2 number 6s for both of its leads, so just meeting the 100 amp requirement on the terminals, and the 4 series prismatics are going to handle 100 amps per cell. We have probably one of the more complex BMSs with the non-rechargeable button cell on it, which is interesting. The Battleborn here has 5 number 10s, so we're talking over 150 amps capacity on the wires, by far the most overbuilt on the wires.
30 parallel 4 series, so definitely the most redundancy in the cells here, and each of these cells is going to handle the least amount of current of the batteries at only 3.3 amps per cell at full load. The LiTime here, 310s, by far the least amount of wiring, actually undersized a little bit, and 1.6 on this side for our entire current. These are probably going to get a little warm. All of these are just in series, the prismatics, so each of these cells is going to handle 100 amps per. The Renogy here, we've got 4 number 10s, so meeting our 100 amp requirement for the wiring. And we have a 4 series 2P configuration here. So each of these cells are going to handle 50 amps on these pouch cells. And then finally on the Dakota here, we've got a 20 parallel 4C configuration on the cells. And we've got 2 number 8s, so kind of right at the limit again on both positive and negative.
A quick note on wiring inside the packs. A lot of times we see multiple wires like this that are all doing the same thing. This is called wiring in parallel, and it's perfectly acceptable to carry more current. However, the size and how many there are still is important because you have to have enough capacity to carry the current. Wires that are too small increase the resistance, can get hot, and cause other issues at high load applications. It's important that wire sizing is correct, and you can also do it with a single wire. Multiple wires, single wire, it doesn't really matter as long as it's done correctly. And we definitely see differences between the battery manufacturers and basically the capacity within the pack and how much resistance you're going to see within these wires.
BMS-wise, relatively simple on the Dakota here with a pretty small amount of FETs and heatsink. We'll see how that handles. Very large BMS here on the Renogy with the largest of our heat sinks. A lot of complexity going on there. The LiTime, very simple BMS. We'll be testing that. The Battleborn's BMS is actually one of the more simple BMSs. You can actually see the bleed resistors, really straightforward. And then probably one of the more complex BMSs, again, with that little funny button cell on the Lion here, but a nice large heatsink. LiTime here is definitely missing a heat sensor. It's only a heat switch for high temperature, so at least it's got that. The Battleborn, did I find its thermal sensor? Okay, so it has a single thermal sensor that goes down, yeah, in between the cells, down here somewhere. We'll dig that out and test that out. And then the 4 thermal sensors on this one. This one has a couple, I think 3 inside this plug here. I'm not sure I'm going to be able to test that one. And then this one just has the single thermal sensor as well. All right, let's get these charged up and let's test those thermal sensors while we're charging it up, because that's one thing we can do. And then we're going to discharge them all and get a capacity. Before we get going, we're going to do a ACIR test on all of these batteries. This is a 1000 Hertz multi-probe, 4-probe ACIR test, and I have calibrated this with my own oscilloscope. So I trust the readings off of this. We're going to ACIR at multiple points throughout these testing.
Before we start, I took voltage and internal resistance measurements on these batteries as they were received. The measurements will give us good insight into the battery's electrical design and performance.
I quickly want to explain cell balance in a pack. Cell balance is basically how similar the cells are to each other. In theory, you basically want to build a pack where all the cells are identical. They all perform the exact same task. If one cell has too much power, too little power, it's going to impact the entire pack depending on its configuration. In cells in parallel, a little bit of unbalance is usually not a big deal because they kind of self-balance, but in cells in series, they have no self-balancing capability. We want them to be as close to the same as possible. Now, the BMS almost always has some balancing function where it can basically push a little bit of current from one to the other and rebalance them voltage-wise. Usually, voltage is the only thing these are looking at. Internal resistance, while it is important that we are very balanced with internal resistance, we really have no control over that within the pack. If it's out of balance with internal resistance from the factory, that's a physical property of the battery that you cannot impact. Voltage, however, can be balanced, and it can help keep the pack more in balance in the long term. However, if we start out with a pack that's not well balanced from the beginning, that's just going to get worse and worse over time. And as the battery ages, you're going to end up with cells that are higher and lower than the rest of them because just the general degradation of the pack causes this degradation or causes the cell imbalance to grow over time. So voltage balance between the cells is really the most important thing that we need to look at when we're looking at the balance of the packs. Internal resistance, I really just wanted to measure because they're brand new and I'm kind of curious to see how similar all the cells are.
This chart shows the maximum discrepancy for voltage and internal resistance, as well as the actual measured values on the cells below the chart. The Dakota cells were particularly hard to get a good internal resistance on due to the pack design, so I'm omitting this data from the chart. As measured values are below, however, and overall they're higher than all the other packs. For the Battleborn, voltage was perfectly balanced, but IR was a little bit higher than others. In general, cylindrical cells have higher IR, which is normal. IR and voltage tests of LiOn, LiTime, and Renogy were all within acceptable limits, as seen in the chart. In general, larger prismatic and pouch cells have lower internal resistance, which is normal. First up for the thermal testing is Battleborn.
So here is test setup number 1. What we've got going on is we've got a MULTIPLUS 3000 that I can use for charging and discharging. I've got a live connection to it so I can change all the different charging parameters. Right now it's off. We're pulling power in from an auxiliary source. The battery is hooked up to it via a Thornwaves Lab PowerMon shunt with data logging at 1 second intervals. And all that data is going to come over here, and we can actually pull up that data log and see a live graph of the voltage, current, and the temperature. Here in the middle, I've got a thermal oh my gosh, what's this thing called? A Peltier cooler that I'm going to be able to vary the temperature of this top piece both up and down. I'm able to vary this temperature via the my power supplies over here. I can vary the voltage here and have very accurate control over the temperature there. And I've got the temperature sensor from the shunt, the temperature sensor from the battery, so we're actually going to be able to see what happens. And this is this little monitor here, so just an easy read off of that. And that line is that blue line right there, and we can just go back and see the temperature right there. We're reading 73 degrees off of this and 73 degrees up there, so we're pretty good. Let's go ahead and start a charge on this. We're going to also charge this battery all the way up so that then we can run it over to the discharge station, and then we'll swap a new battery in to run the same test.
Current lithium-ion batteries should not be charged at low temperatures as it can cause irreversible damage to the cells. Generally, they should stop charging slightly below freezing, but can still discharge. The BMS should prevent this. For high temperature operations, cells actually perform better at both discharge and charge, but degrade far faster. Acceptable upper limits for continuous operations generally considered about 140 degrees Fahrenheit. Above that, cell damage and safety can be compromised, and both charge and discharge should be interrupted.
The battery now thinks it's 46 degrees. There, let's shut off. About 27 degrees. So here's the data log that we're going to capture for each of these tests. So the green is the current, the red is the voltage, and the blue is the temperature. So you can see we came in, we started dropping the temperature, and right here, the current, there we can look at the temperature. We're reading 27 degrees, 28, 27 degrees where it cut out. And then we started warming the temperature up, basically at the very end. 140 degrees. It cut out at 140 degrees on the top. I'm going to go ahead and plot all of these for each of these tests that we're going to run on each of these batteries.
I was able to get the thermal sensor pulled from the Renogy pack and set up on my thermal tester. The Renogy cut out at 28 degrees on the cold side and about 140 for the high temperature disconnect. Dakota cut out at 32 degrees and 148 on the high temp side. LiOn was the most conservative, cutting out around 35 degrees for the cold and 120 for the hot. I do believe my temperature sensor lifted slightly from the bed on this one though, so the temperatures will actually be a little colder and hotter than measured.
For the temperature sensor on this unit, the inside cell thing sensors work, but there are two temperature sensors on either side, but
I took them up to 300 degrees and they still didn't cut out. I was melting the plastic, so we can only assume that the inside ones do anything.
The LiTime did not offer low temperature protection. It's actually a temperature switch, not a temperature sensor, although I did run it down to 22 degrees Fahrenheit and held it with no change. On the high temperature side, it did cut out around 170 degrees. Overall, all passed the tests except for the LiTime on the cold side. I gave it a partial pass on the high side because, well, it did shut down. 170 degrees is a bit warmer than generally accepted by industry standards for cell operation, which is usually around 140. Once all the batteries were fully charged, before running the discharge test, we once again took a look at the voltage and IR on all the cells. Here, things started to get interesting. Once again, our chart shows the maximum voltage and IR discrepancies and has the actual measurements below. With the pack fully charged, it's expected the cells will drift a little due to inconsistencies in actual capacity, and shows how well balanced the pack really is. I pulled the packs off the charger once they were through absorption, or the BMS shut down charging. I did not allow the packs to sit fully charged, which is usually where they self-balance, allowing us to see closer to actual cell balance without pack interference. I also unplugged all the balancing leads before taking these measurements for all of these tests because it could interfere with our IR testing. Battleborn's voltage remained extremely well balanced and IR discrepancy did not change. IR did increase slightly at full charge, which is normal. All the rest of the pack saw some voltage drift and would need to be compensated by the BMS, but were right at the acceptable limits for unbalance. The LiTime, however, showed extreme imbalance in voltage on one particular cell. I reran the tests multiple times and even verified with my oscilloscope and a secondary meter, confirming the extreme imbalance far outside the acceptable range prior to balance.
All right, so this is what our discharge station looks like. We've got the battery hooked up to positive and negative. We've got a pierce negative lead that's giving us measurements for current and voltage off of another Power Mount 5S shunt. What we're doing here is we're dumping all of our load into water. This is just a water tank with a recirculating pump just to circulate the water. We've got 700 watt elements, but one of them I've got on a PWM charge controller so I can vary its current to get an exactly or very close to a 100 amp run. I'm going to set it at 100 amps and leave it, and that will give us our full discharge test. One other thing, we do have a temperature sensor I've got that is just stuck in here. I'm going to find a place on each battery where I can get it deep into the cells, and in this one it's just kind of deep in on this side. So that's our Renogy setup. Charging. 3, 2, 1, bam! 85 amps, turn it all the way up to 100. Just adjust it for the first few seconds because the voltage drops pretty rapidly.
For each of the battery discharges, we will take thermal imagery about halfway through and near the end of the run.
All right, we're at 50% state of discharge on the 100 amp Renogy run. You can see our BMS is the hottest part here. We do have some hot spots on the batteries themselves, but the cells themselves are actually staying nice and cool. One final thermal run on the Renogy. We only have a couple percent left. Voltage is really tailing off. BMS hanging around 170 degrees and 30 on the wires. And the cells themselves got pretty warm now. You can see that we're sitting around 114. Again, taking a peek between those cells. We're at 120 between the cells. You can see they're really heating up in between. There's no way for them to reject the heat.
Voltage and current were very consistent during the discharge, and the battery made 97 amp hours and 1,228 watt hours. Next up is the Battleborn on the discharge station. I mounted the temp sensor on the bottom of the pack, deep inside the cells.
Battleborn pre-energy run. About 50 amp hours in, you can see the top cells are a little bit warm. We're reading almost 100 degrees up there. Got a hot spot down here and here. I think this is because the bolts that actually hold these cells together are up here. So I think this is resistance. This is probably more of what we're actually seeing cell-wise. This is resistance between the cells that's causing them to heat up. That's more a design thing than a cell thing. Our BMS running around 140 degrees inside. Nothing on the resistors. Voltage is tailing off. Battleborn's probably about to shut down. Here we are at the end of the run.
Interestingly, the heat distribution kind of seems to have changed. We still have these hot spots, 115. Our wires are still quite cool. Never got over 100. BMS, 130, about the same as before. Wires still around 100. Again, I think this is more so what the cells themselves are doing. They didn't really warm up a whole ton. It's more so the resistance differential in the connection points.
The current and voltage remained very consistent on the run, and the battery made 100.8 amp hours and 1,232 watt hours.
For the Dakota discharge run, we're putting the temperature sensor on the bottom, similar to how we did the Battleborn. Here's the thermals on Dakota pre-run. Our jug is 100 and some degrees. All right, here's the Dakota at the 50% run. The cells are toasty, 120. You can see quite a bit of heat on the inside there. Our wires are sitting around 130 degrees. And the BMS is 155. This has the fewest amount of FETs of all the BMSs, so I'm not surprised that it's going to be the hottest. 120. See if we can kind of take a peek in between the cells here. 153 in between the cells. All right, Dakota Lithium's almost at the end of its run. It's sitting at 95 amp hours right now. You can see this is very hot. 145 on the cells up there, 160 inside, 164. Whew, hot in between. 160 on that piece of tape there. Wow. 160 on the BMS, 156. That's the heat sink on the top, which is reflective, so we're not seeing the heat. Let's lift this up a little bit. Oh gosh, it is hot. Almost 170. 167. That's some heat coming from the BMS. We can kind of see it there, 150, but it's also just directly from the battery. The Dakota just wrapped up, and man, it's the hottest we've had yet. it's just radiating heat. Just a big block of heat. It came in at 97 amp hours, 1100. Oh, let's see, just kicked back on again. So we'll let it kick off one more time. If they kick back on within a couple minutes, I'll let them do that and discharge just a little bit more. If the voltage recovers. Golly, it's like a bonfire. One more note on this Dakota run. I had this temperature sensor out here, and I just kind of shoved it back in where it was and tried to turn it back on, and it went into thermal shutdown. So technically it would not have been able to complete the run at all in the pack as designed because of that thermal cutout, which is quite interesting. So we pushed the limits of this, but it would not have been able to make the 100 amp. I almost kind of want to do another run. Maybe I'll do the other run on this one without it assembled. All right, Dakota's just starting. I got the temperature sensor just taped to the side. We'll see how it does with it fully encased and the temperature sensors in place. Renogy run, battery's around 70 degrees prior to discharge. Here's the thermals on the battery, only about 50%. So there's some heat coming through the case, but not near as much as we saw inside. So it's just trapping that heat inside. I'm sure this case is just gonna get hotter as it sort of discharges, slowly out into it. But Dakota has shut down. Here's my voltage. 0 volts on the top. Okay, tiny bit. Basically, I lost my data because I couldn't go to the cell because it's all apart. I don't think it even got 50% capacity. I wasn't quite sure when it shut down, but it was around 50%. So, complete failure at 100 amp discharge. This is the LiTime on the discharge bench. This is the LiTime at ambient. You can see there's no heat on the BMS. The cells are a little bit warmer than the surroundings, but that was the heat of the day, so they're just kind of holding a little heat of the day. Here's the LiTime at 50% state of discharge. Looks like our cells are in the 90s. This cable looks weird because it has a sheath over it. That's reflective, so we're going to have to look down here. It's like 120, maybe 130 at the hottest part of this BMS. Alright, we're at the end of the run on the LiTime here. It's just about to shut down. You can see the two center cells are just a little hotter, around 108 than the outside ones, probably because they just can't get rid of their heat in any way whatsoever. BMS really stabilized around 125, 130 degrees. Wires running around 100 degrees. Terminal's actually not too bad. The connectors really stayed nice and cool. These laser welded connectors are pretty good. This 6-gauge wire actually handled the current okay. The backside here.
The voltage, current, and temp had large swings on this pack. Voltage increased during the first part of the run, and there was actually a really weird temperature spike near the beginning that I'm not sure why it happened. My guess is that because I had the temperature sensor mounted at the end of the pack, there was some sort of heat reflection from the inner cells. The pack made 99.3 amp hours and 1,240 watt hours when it cut out.
The wire on run, the temperature sensor, I mounted right here underneath this piece of foam on the top center cells. We've got the Lion Energy discharge run before we turn it on. Battery's sitting around 70 degrees. Ambient temperature around 75 in here. There's a Lion Energy at 50% run, similar to the LiTime. The center two cells are the hottest, probably just because they can't get rid of their heat. 83 at the bottom, 95 at the top. Wires at 95, 105 on these wires. BMS is around 120 at its hottest. The leads on top, 110. We just shut down on the Lion, 109 on the cells. Again, those two middle cells are significantly hotter. In between there, 110, very hard to tell. You know, one thing I could kind of do is I could tip it up, get an idea of what it's like underneath. Check that out. Probably a pretty good estimation. BMS should be cooling already. Yeah, it's already cooling. Shut down a little bit ago. 120, 130. Didn't really get a whole lot hotter from its previous run.
Lion Energy's run was very stable with no weird temperature spike, but I had mounted the temperature sensor in a different position on the cells. Considering these are prismatic, I thought maybe I'd see something similar. The pack made 101 amp hours and 1,280 watt hours, the highest of our tests. Comparing all the data on the runs, the batteries performed well, making or getting close to their ratings. Due to the Dakota overtemp, however, we mark it in red on the chart, as it didn't officially completed. Amp hours and watt hours are slightly different amongst a few of the batteries, showing that the LiTime actually slightly edged over the Battleborn in watt hours, but not amp hours. This indicates its voltage stayed elevated slightly longer, which is one advantage to the large prismatics and large bus bars. Overall, all of the batteries' performance was extremely similar, but this only tells a small part of the story, as all of these batteries are brand new. Once discharged, I took readings of the voltage and IR again. Battleborn amazingly remained perfectly balanced, indicating the cells were extremely well matched from the factory. The cell matching process is long and expensive, but always pays dividends in longevity as balance drifts further as cells age. The rest of the paths were acceptable except for the LiTime, which got even worse, far outside what I would ever consider acceptable balance in a pack. This imbalance will get worse over time, and I expect that if I continued to cycle this pack hard without allowing it to balance, we would start seeing early pack shutdown, as long as the BMS cell monitoring works properly, indicating rapid degradation and possible cell overcharge or discharge if the BMS did not function properly. Out of curiosity, I cut open the second LiTime pack as well and charged it up, and once again found significant imbalances on just one cell.
3.345, 3.570, 3.352. So this cell is considerably under, and this is way over. I wouldn't be surprised if this cell actually stopped the charge.
This chart summarizes the voltage and IR tests. Basically, we want to see the most consistency across all operation. Battleborn did a great job across the board with consistent voltage and IR. Lion and Renogy's voltage and IR drifted a bit, but within what I would consider acceptable. Still far higher than the Battleborn though. Dakota's voltage drift limits remained okay, but the IR was so high, primarily from the pack design, probably due to lacking conductive material or the excessive connections. We saw this result in the extreme temperature rise. While the LiTime started out okay, and my testing showed the BMS can balance the pack well, charge and discharge actually showed imbalance in the cells far outside acceptable range, although mainly in 1 or 2 cells. This really shows how spending extra time sorting cell balance from the factory can have a big impact.
All right, here's the setup for our overcharge over discharge test. Back to the MUDFLAP, I switched to a set of bolted 1/0 so we can carry more current here. We've got an induction cooktop that we're going to be able to ramp up the current as an overdraw to see how it handles it, and we're also going to be able to overcharge the battery and see how it handles it. We'll see where and if they cut out.
The LiTime did not seem to have any current protections on either the charge or discharge sides. I discharged up to 300 amps and held it there until the battery overheated around 220 degrees Fahrenheit and shut down. On the charge side, I held it for a while at the max charge rate, and again, it overheated. For the over-discharge and overcharge currents, the Battleborn performed pretty much as it states on the battery. Above 120 amps, it held it for a while, then shut down. The higher the current beyond that, the quicker the shutdown, allowing for instantaneous load startups only. On the charge side, the battery did take 117 amp input without shutting down. Since I could not go higher than that due to my equipment, I'm not sure if it would shut down. But above 120 is a bit high for charge anyway, as all these batteries are not supposed to take more than a 50 amp charge at regular intervals. The Renogy's discharge held a constant current up to 160 amps before shutting down. On the charge side, it shut down immediately above 100 amps. The Lion Energy did not have any overcurrent protection I could find and pushed it up 270 amps, as high as I could go, and held it there. It did not shut down during my run, but started getting hot. On the charge side, however, it immediately shut down above 100 amps. After this test, I also removed that button cell battery from the Lion to see if it had any impact on the BMS's performance and reran the tests with no change. I'm guessing that cell's there for a clock or memory or the Bluetooth functionality of some sort if the battery completely dies. For Dakota's discharge, it held the current up to about 190 amps before shutting off. I attempted pushing the current higher, and it held 250 amps for a few seconds before shutting off. On the charge side, it had a solid 115 amps cutout.
All right, so we've come to the final test that I want to perform on these batteries, which is a short circuit current test. Now, I'm not sure if these batteries are all rated to do this, but it's something that I feel like a drop-in battery should be able to do. We're going to take a big chunk of wire and just short the battery straight out. Now, I don't think we're actually going to have any like cell issues or fire. The weak point in these batteries is always the FETs, the MOSFETs in the BMS, and they should fail. But technically, they should be able to interrupt this and prevent any issues. I've got a oscilloscope set up. You might be able to see that green trace up on the screen up there. And after we run this, I'm also going to basically pause this and see if we can figure out how quickly the BMS reacts when it sees a short. I'm a little concerned about a few of these batteries because they didn't really seem to have good overcurrent protection. But I've seen the Battleborn shorted out a couple times, always by accident. It's like a wrench going across the terminals when you're installing it or something, and I'm pretty confident that this isn't going to blow up in my face. As precautions, I will be wearing my welding gloves. I am in a flame-proof flight suit right now, and I'll be using my welding mask because basically a short across battery is like, could be like an arc, like you're welding, and this should protect me from any UV. All right, here we go. We'll do the Battleborn first. 3, 2, 1. Oh yeah. Okay, here's the trace. So basically the voltage started to sag, so it dropped all the way to 4.88 volts, and then it spiked to about 24 volts, and that's called a flyback transient. This is basically the closure of the BMS. It detected it and closed in about 20 microseconds. All right, we're gonna go from the one that I was most confident in to the one that I am least confident in and see what happens here. Once again, we've got the O-scope set up. This battery is sitting at 13.1 volts, so relatively low charge. All right, here we go. 3, 2, 1. Nothing. I also didn't get a trace. Am I not making a connection or something? 3 volts out of the battery. The BMS is off or dead. I'm not exactly sure. I think we'll just let this battery sit for a bit and see if it comes back online. Next up is Dakota. Also didn't seem to have overcurrent protection, but maybe like the LiTime, it'll shut down or die. Here we go. 3, 2, 1. Nothing. Once again, like the Battleborn, we have a very similar trace. However, this one took about 75 microseconds. How's this time per division? No, that was 220 on the Battleborn. 831 microseconds. All right, time to short out the Renogy. I've got to use probes to get the trace on this one. 1 tiny spark. All right, the Renogy is the quickest of the ones we've had so far, but the highest voltage at about 26 volts right here. Ion energy. 3, 2, 1. Woo! Probably. It seems like most of these have like a reset period, which is really important because if you have like a arc that just kind of keeps on tapping, that could do a lot of damage. All right, I want to repeat the short circuit test one more time with a smaller piece of wire to see how these batteries would handle a short with a little bit of resistance to it. Still did really good. A little bit worse, so probably a little bit slower to respond, but still worked just fine. Renogy responded really well the first time, so I'm guessing it's going to do fine with this. Nice. Mr. Dakota, you're up next. 3, 2, 1. Oh, jeez. Oh, yuck. Ugh. Ah. Dakota failed that test. Maybe we'll try a little bit larger wire. We'll figure out where it shuts off. All right, same test, the Dakota with a 10 gauge wire. 3, 2, 1. 3, 2, 1. I don't think it shut down. No. Yee. 10 gauge is not enough resistance. Yikes. Let's go bigger. All right, this is a Dakota with a 4-aught short test. 3, 2, 1. There we go. That shut it down. Just needs enough resistance, or maybe it's a current sense. I'm not exactly sure, but definitely slower on the response. The Lion Energy here. Small wire. 3, 2, 1. Huh. Did it ever turn back on? Definitely not on. Do I have to turn it back on or something? All right, the Lion Energy just needed a jump. I just gave it a little jump of power, so basically a charge, and that brought it back to life. So we can go ahead and proceed with this test again. Apparently, if you short out this one, it shuts down. Maybe that's the same issue with the LiTime. We'll try to jump that one back as well. All right, we'll start with the small battery. Visor down. 3, 2, 1. Nice. That worked. And I'm guessing it's going to have to be reset again like that first time. After charging for a bit, the LiTime did come back online, so it is not completely dead. We're going to go ahead and try the short circuit test with the small wire. 3, 2, 1. Yeah, definitely didn't work. We'll go to the 10 gauge, just like we did with the, all right, here's the 10 gauge, short, 3, 2, 1. Oh, we just smoked something in the BMS. This is very warm. All right, 10 gauge short. Doesn't really shut off all the way. Yeah, that's kind of what I thought. Something's going on in that BMS. It's not really shorting out. Let's do the 4-aught and see what happens here. Yeah, look at that. That ain't good. I think we killed it. Let's see. So we got a burned one here and a burned one here. So basically what happens with these boards is that usually one side of the FETs is the discharge. So this will actually stop current out of the battery, and this will stop current into the battery. So on the discharge side, we fried 2 of these, and to me that probably means that these will not stop a discharge now, and this battery will probably go far too low. The charge side still looks okay, so we're actually charging it up now. We're going to see if it stops its charge as it should, but here's the temperature switch that definitely shut this down when we were over currenting drawing this thing. So we're in absorption now. We'll see if it shuts off.
Let's now take a look at a summary of how all the tests performed. Starting with the freeze and heat protection from the BMS, all batteries passed the cold temp protection with the exception of the LiTime. Again, they all passed the high temperature test, but the LiTime going higher than generally considered acceptable. On the overcurrent discharge test, Battleborn had a time shutdown as the current exceeded 120 amps. Renogy shut down around 160 amp draw, but Lion didn't have any shutdown even as I pushed it to 270 amps. Dakota seemed to have a time shutdown of sorts as well once the current exceeded 180 amps. The LiTime didn't show any protection, but overheated quickly with a 300 amp draw. On the overcharge, Battleborn did not shut down at my max 117 amps, but Renogy and Lion shut down at 100 amps, and Dakota at 115. LiTime did not show any protection, and once again overheated with a slightly over 100 amp charge. For the short circuit tests, all batteries passed the high test with a 4-aught wire, but the LiTime did something weird, reading around 3 volts on the battery, and may have damaged the BMS during the test. For the short circuit low test with the small wire, Battleborn, Renogy, and Lion all passed with a 14 gauge wire just fine. Dakota failed the 14 gauge test and the 10 gauge test, requiring a 4 gauge wire to shut down properly. LiTime failed these tests completely, and then the BMS smoked, but it was possibly damaged already from the first short test. As for the discharges, they all did pretty well with no significant differences. This test was done at a 1C discharge rate, which is a tough test. Lion did slightly edge out the top capacity, while Renogy and Dakota did not technically make their ratings. We also considered Dakota a failure because it overheated and would not be able to make its capacity when intact, shutting down at about 50% state of discharge. Regarding thermal performance, Dakota's high internal resistance showed its weakness in the excessive heat buildup. Lion won the coolest temperatures on the wires and BMS, but it was actually the LiTime that ran the coolest cells. It does have to be noted that these packs were not in their cases, which would trap heat further. Battleborn actually had some of the coolest cells during the final test, but a large gradient towards the middle of the cells. This makes sense as cylindrical cells tend to have lower currents overall and dissipate heat well, but excessive or poor connections, as in the Dakota, can mitigate this benefit. As far as pack balance, we already discussed the results, but basically Battleborn really shines here with excellent balance across the tests. LiTime showed its biggest weakness here, with inadequate balance during use.
So in conclusion, can we say that the cheap Chinese battery is equivalent to something like the Battleborn? I would say definitely not. From a capacity perspective, Yes, it actually was. In fact, they all got really similar capacities. And that makes sense. And I would actually hope that they would, because they're all the same chemistry and the cells are technically individually rated at 100 amp hours. So they all should make it. And they did for the most part. However, the obvious failure in the BMS, the imbalance in the cells, the weird pack design, all not great. If they were to upgrade the BMS, would we then have a decent pack? I would still say no, because these cells are so out of balance. And it's just going to get worse over time. I'm going to throw out an opinion here. I don't know this for a fact, but I'm going to guess that these are a B grade cell. I don't remember if they claim them being A grade or not, but a B grade cell is a cell that falls slightly out of spec for whatever reason from the manufacturer. If you're an automotive manufacturer, you're only going to be buying cells that are very, very consistent so that you have the most consistent packs that are going to last the longest. And if you want a consistent pack that's going to last the longest, even in these, they still really need to be well-matched A-grade cells. B-grade cells can be a great cell. Maybe they just have like a scratch or something's off about them visually, or maybe they have a slight internal resistance or capacity degradation. There's also C and D grade cells, which are just worse and worse, basically. But all these cells that are slightly out of spec pile up eventually. And the only way to know whether a cell is A or B or C grade is to actually have the manufacturing data. And unless you're buying cells in massive quantities to build packs or build cars or whatever the heck you're building, you're not going to get that data. So those cells eventually do get sold, usually on marketplaces like Alibaba, or to a manufacturer that's willing to use a B-grade cell. And this is actually a use case where a B-grade cell might be okay. The reason for that is that a lot of times they're still going to make their capacities. But if something's off about them, over time, you're going to have a problem. And that time might be 500 cycles. At 500 cycles, this might have lasted a few years. But it also is going to depend on how it's used. If this is like lightly used, it might last for quite a while. If I was to cycle this hard like I did, I guarantee within a few cycles, we would start having problems with the balance of these cells. Cell balance is enormously important in pack design for longevity, and that's something Battleborn does extremely well. Every single one of these cells that they build goes into a cycling unit, and they figure out exactly what their capacities are, and they match them all up so that you have a well-balanced pack that the BMS doesn't have to do a lot to actually keep it in balance. That's the ideal situation with a pack, and that's something that a manufacturer can do that you can't necessarily at home just by buying a handful of cells. With thousands of cells around, they can properly match these. And it's a very time-consuming and expensive process to do, but it's really the right way to build a pack. This is the wrong way to build a pack, which is probably just slapping together a bunch of random cells and hoping that it lasts a while. The B-grade cells also sell for about half of what a new cell would be, and that's kind of in line with where their pricing is on this pack. Looking at the actual spot price of lithium and what cells are going for, this pack is selling for underneath even that. As far as a reliability thing, definitely wouldn't put this in a situation. I would never recommend this battery to anybody who actually is building a system that it's going to be hard to get them in and out of, or there's a reliability concern with it. The manufacturing brochure actually even said these batteries need to be removed every 6 months or a year or something and rebalanced internally if they're used in like a series configuration, which means they know that they're not balancing well on their own, or they have no series balancing capability on their own. Lots of things I wouldn't recommend about this battery. Let's briefly talk cell type. We've got pouch, prismatic, and cylindrical cells here. There's really no one best cell. They all have their pros and cons. The pouch cells are the most energy dense for their size. However, they are the least protected. They're in a soft plastic casing, basically. They're the most environmentally susceptible, as over time at atomic level, moisture and oxygen can make it through this. I don't think any of us expect our cell phone batteries to last 10 years and still have good capacities. This really needs to be in a additional enclosure, which this kind of was, but it wasn't completely sealed from the elements. So I would be concerned with longevity on this. They also have no constraint for swelling. There is atomic level swelling, and there is gas swelling that happens within these cells as a natural process of lithium charge and discharge cycles that can swell and separate the layers inside there, causing degradation. Prismatic cells get a little bit better with a solid metal case holding it together. However, they have concerns as well, be it that they're so large and we only have 4 in series. If one cell starts to have a problem, that's it. That's going to be your lowest common denominator. You can't go beyond that capacity. If one cell really fails, your pack is done. So we have 2 per in this one, and like 18 per on these. So you get a lot more redundancy with multiple cylindrical cells. Prismatic cells also really should be compressed during their first few cycles to squeeze out the gas. I don't know if that was done on these packs ahead of time. I would hope an expensive, high quality prismatic pack was done that way, but I would doubt it on this. And the manufacturer, I've seen manufacturing data actually from this manufacturer, Eve, that stated that if you don't compress the cells under the first 10 cycles, you're going to see like half life expectancy on them, because gas formation separates the plates in there a little bit and can cause degradation over time. With the prismatics, I'm just not a huge fan of them in these small form factors. We're putting a lot of stress on the cells in a very small space. This is the minimum amount of cells that you can have to possibly create a 12-volt pack, and the most amount of problematic issues you could have with an individual cell causing problems for the whole pack. So not my favorite design. Also, that little microscopic swelling with these hard bus bars, I think it's going to put a lot of stress on these terminals over time. Probably another thing that's going to cause some stress in between these prismatic cells. That brings us to the cylindrical cells. Cylindrical cells being the strongest, don't need any compression from the beginning. They've been around the longest, they're the most proven, and even though they're smaller, they're actually usually rated for much higher currents. And I think that's the reason they are still used in Teslas and Rivians and really high performance applications. Be it that they are so many more in parallel to get the same capacity. There's also a lot of self-balancing that goes on internal to the pack that the BMS doesn't have to do anything with. The BMS only has to manage what's in series. And if it was properly matched from the factory, it has to do a minimal amount of work. Both the Dakota and the Battleborn are cylindrical cells, but they, as we saw, the actual pack design had a lot to do with its performance. The terrible resistance caused such high temperatures and a lot of loss in the Dakota, although its BMS also wasn't a real big fan of, but it did protect it at that high level. Not in the run that I did when I removed the sensor, but when we did that second run, it did shut it down. However, that's disappointing because it's the only pack that actually couldn't do a 100 amp discharge without overheating. The Battleborn is the, I think, sort of simplest of designs. I also really like that they actually included sort of a fuse on this terminal back here, that if it were to get too hot, it melts. And it's the only battery that has anything like that. The drawback to that, of course, is if that goes, your battery's toast. And it'd be hard to repair it. All the fancy stuff with the meters and the Bluetooth and things like that, I think it's a neat feature. However, adding all that to the BMS concerns me a little bit. Just all that extra stuff inside a battery that's hopefully going to last 10 to 20 years. I personally think simpler is better inside the pack. I'd say Renogy with their kind of external Cat 6 connections, maybe they had something there. Maybe we could do like external monitoring to it. But it still seemed like a very complex BMS. Now, I guess if you're looking at what's the use case of this, if you're thinking of it as like basically replacing a lead acid battery, yeah, it's probably going to do better than that lead acid battery, at least energy production wise. Longevity wise, I don't know if I could say that it's going to be any better, because if one of these goes out or your BMS goes out, you're going to lose the whole battery. Whereas at least lead acid is going to kind of tail off and let you know it's dying. This will definitely not do that. It might let the magic smoke out, or it just might stop altogether. Might not charge, might not discharge, or in the case of this one where the BMS failed and I didn't, well, we wouldn't know it maybe if it was enclosed. This pack will not stop discharge now. It'll go all the way down and kill itself. I guess overall, my recommendation is still the Battleborn battery if you're looking for longevity and reliability. It just makes the most sense as a drop-in solution that can be used in so many different applications. I also really like that it's the only pack here that was actually assembled in the US, and the CEO of Battleborn is a PhD in chemistry working on developing the next generation in cell technology to make batteries even better, and hopefully do some of that here in the US. They also had full listings for both the pack and the cells, and the most stringent listings of any of the batteries here, which I think is really important, because that is something that you can rely on to say, okay, this has been tested to all these different means, and say that, yeah, it should be pretty safe. Now, while I'm going to wrap this video up here, I am not done with these batteries overall. I'm going to overvoltage this BMSs and find out where they break, say if they're in series, how high can they go on the voltage. We're going to physically puncture the cells. We're going to see what happens when these batteries are in a dangerous situation, when something goes wrong. Is lithium iron phosphate really as safe as they say, or are we going to see some fire? I'm not sure yet, so you're going to have to stick around to find out. It's been a wild couple weeks testing out these batteries, and I hope that you've enjoyed it as much as I have. I'm going to put links in the description to articles where I will put the actual run data from my testing here if you're interested to dig into it. As always, thank you so much for joining us here on Morton's on the Move. Stay safe, and we'll see you down the road. Bye, everyone.